Okay, all right. So your yearly update on modeling steel structures and fire in OpenSees. So I'm going to try and kind of skip over what we've previously done because there's some really fun and interesting things that we've done over the last year that I want to get to here. Okay, so just to remind you all, there's prescriptive fire protection design and then there's structural fire engineering. So those 1 hour, 2 hour ratings that you're getting out of the International Building Code, that's the prescriptive fire protection design. It's based on a singular fire, usually individual member testing, but it doesn't really consider frame action or use any of our skills as structural engineers or engineers. And so where we focus most of our research is in the structural fire engineering. So looking at building specific fire hazards, considering temperature dependent material properties, load redistribution, and all of the wonderful abilities that we can incorporate into our finite element models. So we've previously developed these benchmarking examples that allow us and allow all of you, if you want to simulate steel structures in fire, simulating thermal expansion, beam behavior, all the way to frame behavior, and comparing the results from OpenSees to other analysis platforms, as well as experimental tests. So we've shown that we can do it in OpenSees. And so really what it comes down to though is, while Laura presented on the lateral force resisting systems in buildings for earthquakes, during a fire, it's really about the gravity system. That's what's resisting your fire loads and fire demands. It's not the lateral force resisting system. And some of our most vulnerable parts of our buildings are really our beam to column, beam to girder connections, our gravity connections. So while we can idealize these as a pin at ambient temperature and non-fire conditions, during a fire, we can't idealize this as a pin because we would completely overestimate the capacity of the building, not including the potential failure that occurred in these connections. And miss out on why our steel structures are actually collapsing. So, so all of our previous benchmark examples idealize our connections as pinned. And what we've been doing over the last year is developing a component model that we can integrate into OpenSees that actually does consider all the failure mechanisms of gravity connections during a fire. So that's what I'm going to talk about today. So just to give you some idea of the complexities of this situation, why we cannot idealize this as a pin. So we have our shear tab connections here. When we design these for gravity loads, we design them only for vertical shear. But as we begin to heat up this beam, we're going to have thermal expansion. So we're going to have axial compression in our connections. And around temperatures below 400 degrees Celsius, we're really not seeing much change in our material properties of the steel. But as we continue to heat this beam up, we are going to see degradation of our material properties of the bolts and the plates and the beam itself. Bolt steel and plate steel degrade with increasing temperature differently. So being able to incorporate that into our designs is pretty critical. It also means that we're going to shift failure mechanisms from our ambient design to our fire design. But what also happens at these higher temperatures is the bottom flange of the steel beam will come into contact with the steel column. And therefore, we don't have that free rotation that we assume with our idealized pin anymore. Rather, we're imposing flexural demands in our connections. So now we have these connections that have only been designed for shear have now experienced axial compression force as well as flexure. And eventually we will consume all the fuel in our compartment and our fire will begin to decay. The steel material properties will begin to reduce and we will have thermal contraction, putting tensile forces into these connections during the cooling phase. And so again, these connections we're only designing for shear force are experiencing all these additional demands. And we see failure under each of these demands. So if we are idealizing our connections as pure pins in our finite element models, we are neglecting all these potential demands that can cause failure in our connections. So that's why it's important to incorporate these component models. So what we've done, and I will summarize this quite quickly for you, is we identified the active components in our connection. So what are those individual failure mechanisms that we want to actually simulate? We did a pretty deep dive into all of the component models that are existing out there, as well as some of the experimental tests on isolated connections. And we pulled together our force deformation relationships for each of these components, assembled them, and then benchmarked them against experimental tests. So active components. So we are focusing on this weld of our shear tab to our beam, so that we can actually have weld fracture between the shear tab and the column itself. We identified this gap as an active component. Once that gap closes, we'll have local buckling in the beam bottom flange, as well as imposed flexure in the connection. And then all of the failure mechanisms that are associated with our bolts and our bolt holes. So bolt shear fracture, as well as bolt bearing, both on the shear tab and on the beam web. So if we take that connection over on the left and we idealize all of these active components as zero-length spring elements on the right, which is what I'm showing, we can actually start building up our connection and assembling this connection through our component model. So each of these springs has its own force deformation relationship that I'll explain in a second. But we can start building this all up so that we can actually simulate all these different failure mechanisms in our connection and actually be able to simulate all those behaviors that I was talking about earlier. So we can simulate that gap closing on the bottom. We can simulate bolt bearing and bolt shear fracture, as well as potential unzipping of that weld during the fire itself. We did perform a sensitivity analysis on how many springs we actually need to include for that column weld. I'm not going to present that today. That can be another presentation, but you know, with all this, there's a lot that kind of went into sleuthing out how to actually assemble this together and what these force deformation relationships are. So when it comes to bolt shear, traditionally, what has been assumed in these component models is that the bolt shear fracture is the same regardless of the temperature. But what actually happens is that bolt shear fracture is really brittle at ambient temperature on non-fire conditions. I think we all know that in this room. But what happens at elevated temperatures is it actually becomes quite ductile. The fracture surface changes, and we are seeing that the bolt is capable of more deformation at elevated temperatures. So while it's not capable of transmitting as much and resisting as much load, it does have more ductility at elevated temperatures. And so we incorporate that into our bolt shear constitutive model to be able to capture that behavior at different temperatures, that brittle behavior at temperatures below 400 degrees Celsius, and then that ductile behavior at temperatures above 400 degrees Celsius. For the bolt bearing behavior, we do see kind of the same ductility at every single temperature, and we see this in our experimental tests that have been performed previously. But other researchers have actually not included any post-peak behavior in their bolt bearing constitutive models. Rather, they just assume that the bolt holes will just continue to resist load in perpetuity, and the bolts will eventually fail in shear. But we do see tear out failure of our connections and of our plates, and so we did include post-peak behavior here in this constitutive model. When it comes to that beam bottom flange bearing on the column itself, we've seen two different models, and I'm going to show you the implications of these two different models in our benchmarking example. The first is that once that bottom flange hits the column, we have infinite stiffness and no additional rotation. The other model is actually being able to simulate that beam bottom flange buckling and limit the force transfer that can occur through that connection because of that beam bottom flange buckling. And then lastly is our weld capacity. So we used the ductility that is suggested through AISC as our deformation limit, and included a brittle fracture for our weld capacity. Okay, so we've identified our active components, we've defined our force deformation relationships, we've assembled these all together, and now it is time to benchmark these against some experimental tests. And so there's both isolated experiments and the full-blown structural system. So isolated experiments have occurred at steady state. Researchers have heated specimens to a specific temperature and then loaded until failure. They've loaded until failure at different angles to the stub beam itself, and I'll show you what that looks like in a second. And so that allows us to actually benchmark our assembled component model against different temperatures and different loading angles, seeing how we're doing in being able to simulate this. Whereas our structural system is tested in transient heating, meaning it's loaded first and then heated until failure. And that allows us to look at the shear tab in the full system. Okay, so first isolated experiment. So this is the first isolated experiment. It was performed at University of Texas under Mike Engelhardt. So we have this stub beam connected to a plate, and it's just loaded in parallel to the direction of the beam itself. So perpendicular to the connection itself in pure axial force. So this allowed us to just look at pure temperatures on the connection loaded just axially. The second one is a stub beam, stub column, and this is put into a furnace, heated to a set temperature, and then loaded at a specific angle. So this allows us to look at that combination of forces, so axial force and flexure put into the connection itself. All right, so first looking at those tests performed at Texas, we're able to see that our component model does a really good job of actually simulating that ductility as that deformation, as well as the maximum force in the connection. We're able to simulate maximum force in the connection with our component model under bolt bearing. We missed the mark a little bit in terms of the deformation, but with regards to capacity of the connection, which is our ultimate goal, we were able to hit that. When it comes to loading at different angles, our component model is able to actually simulate those behaviors at different angles and different temperatures that are realistic during a fire, as well as simulate that post-peak behavior, most importantly, of these connections. Okay, so taking that component model and putting it into a structural system. NIST performed some experiments on composite beams. This is a 42-foot long composite beam, W18 by 35 girder with a composite slab connected to columns. All of those members outside of the columns are there for bracing of the column to prevent any out-of-plane movement of that column. And it's loaded at 6 locations along the beam. All right, so they collected a lot of data. That data is readily available, but we also collaborated with them to gain access to some of the more processed data, so that we can get it, we can access it a little bit quicker. And we simulated these experiments in 8 different ways. The first being assuming an idealized pin connection. We wanted to know how effective is our connection model in being able to simulate the connection rotation as well as forces in the connection. And then we varied different parameters along the way. I'm not going to present all of these. I'm only going to show you the pure pin connection as well as what happens when we do and do not consider that, that local buckling of the bottom flange of the beam in the connection. Okay, so this is the axial force in the connection over the time of the fire. The solid black line is the experimental data. The dashed black line is a purely pinned connection. So You can see that does not align with the data at all. We can see when the gap actually closed around 35 minutes, the gap closes between that beam and the column. This gray dotted line is if we do not consider beam local buckling of the bottom flange, and the solid gray line is when we do. So we can see that we are getting closer to the actual axial force in the connections if we are actually considering limiting that because there's damage in the beam. And then, the last part I'll show you is the rotation of the connection. So the connection actually fractured there was weld fracture in the connection. So if we focus on the bottom where there is no fracture first, again, black line is the experimental data. We're able to actually hit that maximum connection rotation when we do actually consider estimating local buckling of the bottom flange rather than just allowing infinite stiffness of that bottom flange. We played around with this weld constitutive model for a really long time, and we definitely need further development to be able to actually simulate that unzipping of the weld that we're seeing during these tests. All right, so to just wrap up, we were able to simulate connection capacity as well as rotation and post-peak ductility and post-peak behavior in these isolated connection tests, as well as axial forces in the connection and local beam damage in the NIST experiments. We need some better understanding of weld failure during a fire. There's very limited experimental data on this to feed into our constitutive models. And then we actually assumed 100% composite action of the beam, but that's not exactly what happened at all. In fire, there's actually temperature dependent force slip behavior of shear studs that we have not included into our composite beam model that might allow the two to align a bit more. So a lot of the work I just presented was of the master's thesis work of James Gordon and Walker Matalozzo. Just thanking Michael Scott and Kevin Mackey for helping us slew through source code of OpenSees. And this is actually a collaborative funding between AISE and PEER. So thank you.